Hello everyone, I am Dr. Abhina Shirley, Assistant Professor from the Department of ECE at SRM IST Katangalattu. In this video, we are going to learn about cloud resource virtualization, which is one of the core technologies behind cloud computing. We will understand how virtualization allows multiple operating systems and applications to run on a single physical machine, helping organizations improve efficiency, reduce cost, and utilize resources effectively. In this unit, we will cover important concepts related to virtualization. We will begin with the basics of virtualization and layering concepts. Then we will study virtual machine monitors, also called hypervisors, and understand how virtual machines work. We will also discuss in performance isolation different virtualization approaches such as full virtualization and para-virtualization, and finally hardware support for virtualization technologies. The concepts discussed in this unit are referred from the book Cloud Computing Theory and Practice by Dan C. Marinesu. In particular, we will focus on Chapter 10, which is based on cloud resource virtualization. Let us understand what virtualization actually means. Virtualization in computing is the process of creating a virtual version of hardware and software using software technologies. Instead of depending completely on physical machines, we create virtual environments inside a computer. The main components involved are virtual machines, resource allocation, and the hypervisor. A virtual machine behaves like an independent computer. For example, one virtual machine can run Windows, another can run Linux, and another can run Unix, all inside the same physical system. The system resources such as CPU, memory, and storage are divided and allocated to each virtual machine based on the requirements. To manage all these virtual machines, we use a software layer called a hypervisor, which controls and monitors the virtual machines. Think of virtualization like a large apartment building. The physical server is like the entire apartment building. Inside the building, there are multiple apartments. Each apartment is separate and independent, just like a virtual machine. Different families can live in different apartments. Similarly, different operating systems like Windows or Linux can run in different virtual machines. The building manager is like the hypervisor. The manager allocates water, electricity, and maintenance to each apartment, just like the hypervisor allocates CPU, memory, and storage to each virtual machine. Even though everyone shares the same building, each apartment functions independently. In the same way, virtualization allows multiple virtual systems to share one physical machine efficiently. Before virtualization became popular, businesses usually followed a one server for one application approach. That means each application required a separate physical machine. For example, the email service might run on a Windows server, the web application on a Linux machine, and the database on a Unix system. At first, this method looked simple and organized, but in reality, many servers were not fully utilized. Most of the time, the systems used only a small portion of their processing power while still consuming electricity, storage space, and maintenance cost. It is similar to using one entire classroom for just one student. Even though the room has many benches and facilities, most of the resources remain unused. In the same way, traditional server usage resulted in poor resource utilization and higher infrastructure expenses. Virtualization solves the problems seen in the traditional model. Instead of using separate physical servers for different applications, virtualization combines multiple servers into a single powerful physical machine. Inside that machine, multiple virtual environments can be created to run different operating systems and applications independently. Because of this consolidation, the available resources are utilized much more efficiently. It also reduces the amount of physical hardware required, which lowers cost, saves space, and reduces power consumption. At the same time, virtualization provides better scalability and flexibility. New virtual systems can be created easily whenever required, making testing, development, and deployment much simpler. You can think of it like combining several small shops into one large shopping complex. Even though everything exists inside one building, each shop still works independently while sharing common resources like electricity, security, and maintenance. In the same way, virtualization allows multiple systems to share one physical server efficiently. This slide shows how a single physical server can run multiple virtual machines at the same time. Here, one server is running four different virtual machines, and each virtual machine can run its own application and operating system independently. Instead of keeping separate physical machines for every application, all of them are consolidated into one system. This leads to efficient utilization of CPU, memory, and storage resources. At the same time, virtualization reduces hardware dependency, improves scalability, and provides isolation between applications. Even if one virtual machine faces an issue, the other virtual machines can continue running independently. You can compare this to a modern smartphone where multiple apps run simultaneously, like YouTube, WhatsApp, and Google Meet. Even though all the apps share the same phone hardware, each application works independently without affecting the others. Similarly, multiple virtual machines share the same physical server while functioning like separate systems. Next, we will look on to hypervisor. A hypervisor, also called a virtual machine monitor, is the software responsible for enabling virtualization. Its main role is to create, manage, and monitor virtual machines. It acts like a bridge between the physical hardware and the virtual machines running on top of it. The hypervisor allocates important system resources such as CPU, memory, and storage to different virtual machines based on their requirements. In this way, multiple virtual machines can share the same hardware efficiently and in a controlled manner. You can think of the hypervisor like a hotel manager. The hotel is the physical server and the rooms are the virtual machines. The manager decides how resources like electricity, water, and room allocation are shared among the guests. Similarly, the hypervisor manages and distributes computing resources among different virtual machines. Next, types of hypervisor. Hypervisors are mainly classified into two types, type 1 hypervisor and type 2 hypervisor. A type 1 hypervisor, also called a bare metal hypervisor, is installed directly on the physical hardware. Since it does not require a separate operating system, it provides better performance and efficiency. These hypervisors are commonly used in data centers and enterprise cloud environments. On the other hand, a Type 2 hypervisor runs on top of an existing operating system such as Windows or Linux. It is easier to install and commonly used for development, testing, and personal use. However, because it depends on the host operating system, its performance is slightly lower compared to Type 1. You can compare this with transportation. A Type 1 hypervisor is like driving your own car directly on the road, giving better speed and control, whereas a Type 2 hypervisor is like traveling in a bus. It is easier and more convenient for general use, but it depends on another system for operation. This slide explains the basic steps involved in setting up a Type 1 hypervisor environment. First, a physical server is selected. Then, virtual machines are created based on the requirement. After creating the virtual machines, resources such as CPU, RAM, and storage are allocated to each virtual machine. Once the resources are assigned, operating systems like Windows, Linux, or Unix are installed inside the virtual machines. Finally, the required applications such as email servers, web servers, or databases are deployed within those virtual machines. Since the hypervisor runs directly on the hardware, the entire setup becomes more efficient and suitable for enterprise environments. It is similar to constructing a new apartment building from the ground level. First, the building is prepared, then separate apartments are created, utilities are allocated, and finally different families move in and start using the rooms independently. This slide explains the working steps of a Type 2 hypervisor. Here, the process begins by installing a host operating system such as Windows, Linux, or Mac OS on the physical computer. After that, the hypervisor software like VMware Workstation or VirtualBox is installed on top of the host operating system. Inside the hypervisor, virtual machines are created and resources such as CPU, RAM, and storage are allocated to them. Then, guest operating systems are installed inside each virtual machine, followed by the required applications. Since the hypervisor depends on the host operating system, this method is easier to use and is commonly preferred for testing, learning, and development purposes. You can compare this to installing different apps on a smartphone. First, the phone's operating system must be available. Then, applications are installed on top of it and use the phone's resources. Similarly, in Type 2 virtualization, the hypervisor works on top of an existing operating system. This slide explains the importance of virtualization in real-time applications. In modern computing environments, organizations need systems that are flexible, scalable, and efficient. Virtualization helps achieve this by allowing multiple virtual systems to run on a single physical server. It reduces hardware usage, lowers infrastructure cost, improves resource utilization, and makes system management easier. It also supports quick deployment, easier maintenance, and better reliability in real-time applications. For businesses and cloud service providers, virtualization plays a major role in improving performance while reducing operational complexity. You can think of it like public transportation. Instead of every person using a separate vehicle, many people can travel efficiently using one bus or train. In the same way, virtualization allows multiple applications and operating systems to efficiently share the same hardware resources. One of the major advantages of virtualization is portability. If a physical machine becomes old or outdated or runs out of storage and processing capability, the virtual machines running inside it can be easily moved to another more powerful system. Since virtual machines are software based, migration becomes much simpler compared to moving an entire physical setup. This improves flexibility and reduces downtime during upgrades or maintenance. You can compare this to moving a file from an old laptop to a new laptop using a pen drive or cloud storage. The file continues to work without needing to be recreated. Similarly, virtual machines can be transferred from one physical server to another with minimal difficulty. Full computing capability. Today's computers and servers are highly powerful, but in many situations, their resources are not fully utilized. Virtualization helps in using the complete computing capability of a system by allowing multiple virtual machines to run on the same physical hardware. Each virtual machine can perform different tasks independently while sharing the available resources efficiently. This improves overall hardware utilization and helps organizations maximize system performance without purchasing additional machines. You can think of it like a large auditorium that remains mostly empty for a single meeting. Instead of using it for only one small group, the space can be divided and used by multiple teams at the same time. Similarly, virtualization ensures that the available computing power is fully utilized rather than remaining idle. Disaster and recovery. Virtualization also provides strong support for disaster recovery and backup management. Since virtual machines are stored as software files, they can be easily backed up, copied, and restored whenever required. These virtual machine files can also be uploaded to multiple physical machines for safety and reliability. If a system failure occurs, the virtual machine can quickly be recovered and restarted on another server, reducing downtime and data loss. You can compare this to saving important documents in cloud storage. Even if your laptop gets damaged, the files can still be accessed and restored from another device. Similarly, virtual machines can be recovered easily because they exist as software-based files. In virtualization. Virtualization is not limited to just computers or servers. It can be applied across different layers such as access, applications, processing, networks, and storage. Along with these layers, security and centralized management are also very important. Each layer performs a specific function and together they create a complete virtualized environment that is flexible, scalable, and easy to manage. You can think of it like a multi-storage shopping mall. Different floors are dedicated to different purposes such as shopping, food, entertainment, and security. But all of them work together as one complete system. Similarly, different virtualization layers handle different tasks while supporting the overall cloud infrastructure efficiently. This slide explains the 7-layer model of virtualization. The first layer is access virtualization, which allows users to access applications and data from any device or location. The second layer is application virtualization, where applications run independently without depending completely on the operating system. The third layer is processing virtualization, which enables multiple virtual machines to share the same processor and memory resources. The next layer is network virtualization, which creates virtual networks independent of physical hardware, improving flexibility and isolation. The fifth layer is storage virtualization, where multiple storage devices are combined into a single logical storage system for easier management. The sixth layer focuses on security for the virtual environment, ensuring protection through isolation, encryption, and access control mechanisms. Finally, the seventh layer is management of the virtual environment, which provides centralized monitoring, automation, and control of all virtual resources. You can compare this to the functioning of a university campus. Different departments such as academics, laboratories, library, transport, security, and administration perform separate tasks, but together they ensure the smooth functioning of the institution. Similarly, each virtualization layer has a specific role, but all layers work together to support the cloud environment. Next, moving on to virtual machines. A virtual machine is a software-based version of a computer. It behaves like a real physical system and has the ability to run operating systems, applications, and store data independently. Even though it is created using software, it functions just like a separate computer inside a physical machine. Each virtual machine works in an isolated environment, meaning one virtual machine does not directly interfere with another virtual machine running on the same hardware. This allows multiple operating systems and applications to run simultaneously on a single physical server in a secure and efficient manner. You can think of a virtual machine like a separate workspace inside a large office building. Even though many employees work in the same building, each person has their own cabin, files, and systems to work independently. Similarly, each virtual machine behaves like its own computer while sharing the same physical hardware. What are virtual machines used for? Virtual machines are used in many real-world computing applications because they provide flexibility, isolation, and easy management. They are widely used for building and deploying cloud applications. Developers also use virtual machines to test new operating systems, including beta versions, without affecting the main system. Virtual machines make development and testing easier because new environments can be created quickly whenever required. They are also useful for backup and recovery purposes. Older operating systems can be installed inside a virtual machine to run legacy applications and suspicious or virus infected files and can be tested safely in an isolated environment. Another important advantage is compatibility. Applications designed for one operating system can sometimes be run inside a virtual machine using a different operating system. You can compare this to a science laboratory in a college. Different experiments can be performed safely in a separate lab setup without disturbing the others. Similarly, virtual machines provide separate environments for testing, development, security analysis, and application deployment. Types of virtual machines. A virtual machine is an isolated environment that behaves like a complete computer, even though it uses only a portion of the physical system resources. A process virtual machine is created for a specific application or process and exists only while that process is running. Once the process ends, the virtual machine is destroyed. A system virtual machine supports a complete operating system along with multiple user applications similar to a real computer. Traditional virtual machines run directly on hardware and support multiple virtual machines efficiently. Hosted virtual machines run on top of an existing host operating system. Hybrid virtual machines combine features of both approaches by sharing hardware resources with the host operating system while also supporting virtualization. You can compare these virtual machines types to different types of accommodation. A hotel room used temporarily by a traveler is like a process virtual machine because it exists only for a short duration. A permanent apartment where a family lives and performs daily activities is similar to a system virtual machine. In the same way, different virtual machines are designed for different purposes and usage environments. Benefits of using virtual machines. Virtual machines provide several important benefits in cloud and computing environments. The first advantage is cost savings. Since multiple virtual machines can run on a single physical server, organizations can reduce the number of physical systems required. This lowers hardware, electricity, and maintenance cost. The next benefit is agility and speed. Virtual machines can be created, configured, and deployed quickly, making development and testing much faster. Virtualization also helps in reducing downtime. Virtual machines can be migrated easily between servers, and backup and recovery processes become much simpler during failures. Another major advantage is scalability. Organizations can easily increase resources or create additional virtual machines whenever workload increases. Virtual machines also improve security because each virtual machine operates in an isolated environment. This allows risky applications or malware analysis to be performed safely without affecting the main system. You can compare this to a modern co-working office space. Different teams can work independently in separate cabins while sharing the same building infrastructure. It reduces cost, improves flexibility, and allows easy expansion whenever new teams join. Performance isolation is an important concept in virtualization because multiple virtual machines share the same physical hardware. To ensure that one virtual machine does not negatively affect another, the hypervisor carefully manages system resources. The first aspect is resource allocation, where CPU, memory, storage, and network resources are distributed among different virtual machines based on their workload requirements. Next is resource scheduling, which controls when and how virtual machines use the hardware resources so that conflicts are avoided. Resource monitoring continuously tracks system performance and identifies bottlenecks. Based on this, resources can be reallocated or virtual machines can be migrated if necessary. Another important concept is quality of service, where critical applications are given higher priority to maintain better performance. Isolation mechanisms also play a major role by preventing one virtual machine from interfering with another through techniques like CPU scheduling, memory protection, and network traffic control. Finally, performance guarantees help maintain minimum service levels such as CPU performance, memory response time, disk speed, and network bandwidth. You can compare this to a hotel where many students share common facilities like electricity, Wi-Fi, and water. Proper scheduling and allocation ensure that one student's usage does not disturb the others. Similarly, virtualization manages resources carefully so that all virtual machines perform efficiently. Next, moving on to approaches in virtualization. The concepts discussed here are referred from the book Essentials of Cloud Computing by K. Chandrasekaran. In this section, we will study three important virtualization approaches, that is full virtualization, para-virtualization, and hardware-assisted virtualization. Each approach has its own method of managing virtual machines and interacting with hardware. Some techniques focus on better compatibility, while others focus on improving performance and efficiency. Understanding these approaches is important because they form the foundation of modern cloud computing and virtualization technologies. First, let us discuss full virtualization. Full virtualization is a technique in which virtual machines behave exactly like real physical computers. Each virtual machine runs its own guest operating system independently, and the guest operating system is completely unaware that it is running inside a virtual environment. A hypervisor, also called a virtual machine monitor, manages the interaction between the guest operating system and the physical hardware. The guest OS cannot directly access the hardware, so the hypervisor acts as an intermediary. To make virtualization possible, techniques like binary translation and direct execution are used. Binary translation converts sensitive instructions so that the guest OS can run properly in the virtual environment. Full virtualization provides strong isolation and security between virtual machines. It also allows multiple operating systems to run on the same hardware without modifying the guest operating system. You can compare this to watching a realistic simulation game. Inside the game, every character behaves as if it is living in a real world, without knowing that the entire environment is actually controlled by software running behind the scenes. Similarly, in full virtualization, the guest operating system behaves like it is running on real hardware. This diagram shows the architecture of full virtualization. At the bottom, we have the physical hardware components such as the processor, memory, and storage devices. Above the hardware, the hypervisor or virtual machine monitor is present. This layer controls access to the hardware and manages all the virtual machines. On top of the hypervisor, multiple virtual machines are created. Each virtual machine contains its own guest operating system and applications. The important point here is that the guest operating systems do not communicate directly with the hardware. Instead, every request passes through the hypervisor, which acts as an intermediary and manages resource sharing securely. Because of this architecture, multiple operating systems can run independently on the same physical server while maintaining strong isolation between them. You can compare this to students working in different computer labs through a lab instructor. The students cannot directly control the main server or hardware resources. Instead, the instructor manages and allocates access to everyone in an organized manner. Similarly, the hypervisor manages communication between virtual machines and the physical hardware. This slide explains the important features of full virtualization. The first feature is the hypervisor layer. The hypervisor directly interacts with the physical hardware and provides a platform for running multiple virtual machines. Another important feature is complete isolation. Each virtual machine operates independently, which improves security and prevents interference between virtual machines. Full virtualization also supports multiple operating systems on the same hardware. For example, one virtual machine can run Linux while another runs Windows. A key feature is guest OS transparency. The guest operating system is unaware that it is running in a virtual environment and behaves as if it is using real physical hardware. Hardware abstraction is also important because the guest operating system cannot access hardware directly. All interactions happen through the hypervisor. Finally, the hypervisor manages resource allocation by distributing CPU, memory, storage, and network resources dynamically among virtual machines based on workload requirements. You can compare this to passengers traveling in separate compartments of a train. Even though everyone uses the same train engine and track, Each compartment functions independently and passengers may not even notice how the entire system is being managed behind the scenes. Similarly, virtual machines share hardware resources while operating independently. Full virtualization provides several important advantages. One important advantage is strong isolation between virtual machines. If one virtual machine experiences a problem, the other virtual machines continue to operate independently. It also supports multiple operating systems running simultaneously on the same hardware without modifying the guest operating system. This makes installation and usage easier. Another benefit is portability. Virtual machines can be migrated easily from one physical system to another. However, full virtualization also has some disadvantages. Since binary translation is used, additional overhead is introduced which can reduce overall system performance. It also requires a proper combination of compatible hardware and software to function efficiently. Common examples of full virtualization platforms include VMware ESX and VirtualBox. Next, let us move on to the para-virtualization. Para-virtualization is a virtualization technique in which the guest operating system is aware that it is running inside a virtual environment. Unlike full virtualization, the guest operating system communicates directly with the hypervisor using special instructions called hypercalls. Because of this direct interaction, there is no need for binary translation, which improves overall performance and efficiency. However, to support this approach, the guest operating system must be modified so that it can work with the hypervisor. In pair virtualization, the hypervisor and guest operating system work together cooperatively. User applications still function normally, but system level communication becomes faster and more optimized. This approach reduces virtualization overhead and provides better performance compared to full virtualization. You can compare this to students working with a lab assistant during an experiment. Instead of waiting for instructions to be translated through multiple people, the students directly communicate with the assistant who manages the equipment. Because of this direct coordination, the work becomes faster and more efficient. Similarly, in paravirtualization, the guest OS directly interacts with the hypervisor using hypercalls. This diagram shows the architecture of paravirtualization. At the bottom, we have the physical hardware, which includes components like the processor, memory, and storage. Above the hardware, the hypervisor is present. Unlike full virtualization, here the guest operating systems are aware of the hypervisor. The guest operating systems communicate directly with the hypervisor using hypercalls instead of depending on binary translation. Because of this direct interaction, system performance becomes faster and more efficient. Applications run on top of the guest operating system just like in a normal computer environment while the hypervisor manages hardware access and resource sharing. The important idea in this architecture is cooperation between the guest OS and the hypervisor, which helps reduce overhead and improves efficiency. You can compare this to employees directly coordinating with the project manager instead of sending requests through multiple departments. Since communication is more direct, tasks are completed faster and with less delay. Similarly, paravirtualization improves performance through direct communication between the guest operating system and the hypervisor. This slide explains the important features of paravirtualization. Similar to full virtualization, paravirtualization also uses a hypervisor layer. However, in this case, the guest operating system is aware of the hypervisor. One important feature is improved performance. Since paravirtualization eliminates the need for binary translation, virtualization overhead is reduced and system efficiency becomes better. Another key feature is guest OS modification. The guest operating system must be modified to replace normal hardware instructions with hypercalls. These hypercalls allow the guest OS to communicate directly with the hypervisor for operations like CPU and memory management. Paravirtualization also follows a collaborative approach where the guest operating system and hypervisor work together for optimized interaction and faster execution. You can compare this to a smart classroom where students and teachers communicate directly through a digital learning platform. Because everyone is connected and aware of the system, communication becomes faster and more efficient. Similarly, para-virtualization improves performance through direct cooperation between the guest OS and the hypervisor. Para-virtualization offers several advantages compared to full virtualization. One major advantage is improved performance because it eliminates the overhead caused by binary translation. Since the guest operating system directly communicates with the hypervisor through hypercalls, the system becomes faster and more efficient. It is also simpler to implement because it does not always require specialized hardware support. However, para-virtualization also has some disadvantages. The guest operating system must be modified, which introduces additional complexity. Another limitation is portability. Since the guest OS is modified specifically for virtualization, it may not run properly on normal physical hardware. Para-virtualized systems may also face compatibility and migration issues when moving between different hosts or environments. Common examples of para-virtualization platforms include Zen and VMware ESX Server. You can compare this to a sports team trained with a special strategy designed for one particular stadium. The strategy improves performance in that environment, but the same setup may not work easily in a completely different stadium. Similarly, para-virtualization improves efficiency but reduces compatibility and portability. This slide compares full virtualization and para-virtualization based on different aspects. In full virtualization, the guest operating system does not require any modification, whereas para-virtualization requires the guest OS to be modified to support hypercalls. When we consider performance, para-virtualization is generally faster because it allows direct interaction with the hypervisor. Full virtualization may have slightly lower performance due to emulation and binary translation overhead. Full virtualization provides stronger isolation because each virtual machine behaves completely independently. In para-virtualization, the guest OS is aware of the virtualized environment. Full virtualization supports a wide variety of operating systems, while para-virtualization works best with compatible or modified operating systems. In terms of hardware interaction, full virtualization emulates complete hardware, whereas para-virtualization uses hypercalls to request hardware services from the hypervisor. Resource overhead is also different. Full virtualization has slightly higher overhead, while para-virtualization reduces overhead and improves efficiency. Examples of full virtualization include VMware, Hyper-V, and VirtualBox. Examples of para-virtualization include Xen, KVM, and QEMU. This slide introduces different implementations of system virtualization. System virtualization refers to the practical methods and technologies used to create and manage virtual machines on physical hardware. Different virtualization platforms implement virtualization in different ways depending on performance, compatibility, security, and hardware support requirements. Some implementations focus on full virtualization where the guest operating system is completely isolated from the hardware. Others use para-virtualization or hardware-assisted virtualization to improve efficiency and reduce overhead. These implementations form the foundation of modern cloud computing environments because they allow multiple virtual systems to run efficiently on shared hardware resources. This slide explains the importance of hardware support in virtualization. Modern processors include special virtualization features that directly support virtual machine operations. Instead of depending completely on software techniques, virtualization tasks can now be handled more efficiently by the hardware itself. This reduces overhead, improves execution speed, and provides better resource management in virtualized environments. Major hardware companies like Intel and Advanced Micro Devices provide virtualization technologies such as Intel VTX and AMD V to support hardware-assisted virtualization. Because virtualization support is built directly onto the processor, virtual machines achieve better performance, scalability, and efficiency compared to software-only virtualization approaches. This diagram illustrates how hardware support is integrated into virtualization. At the bottom, we have the physical processor and hardware resources. Modern processors include built-in virtualization extensions that directly support virtual machine operations. Above the hardware, the hypervisor interacts with these virtualization features to efficiently manage virtual machines. Because the processor itself supports virtualization, many operations can be executed faster with reduced software overhead. This architecture improves memory management, device access, resource allocation, and overall virtual machine performance. The main idea is that virtualization is no longer handled only by software, the hardware itself actively assists in managing virtual environments. You can compare this to a smart elevator system in a modern building. Instead of a person manually controlling the elevator movement, the system itself automatically manages floor selection and movement efficiently. Similarly, hardware-assisted virtualization allows the processor to directly support virtualization tasks, making the system faster and more efficient. This slide explains some important aspects of hardware-assisted virtualization. The first aspect is virtualization extensions provided by processor manufacturers. Technologies such as Intel VT and AMD V allow processors to directly support virtualization operations. Features like VTX and VTD from Intel and AMD VI from Advanced Micro Devices improve CPU and input-output virtualization. The second aspect is memory management. Hardware-assisted paging techniques such as extended page tables help virtual machines translate virtual memory to physical memory more efficiently, improving speed and reducing overhead. Another important feature is input-output virtualization. This allows virtual machines to communicate efficiently with hardware devices such as network adapters, storage devices, and USB devices. Technologies like direct memory access transfer data directly between memory and devices without heavily involving the CPU, which improves performance. One important feature is nested virtualization, where a virtual machine can itself run another virtual machine inside it. This is especially useful for testing environments, research, and advanced cloud setups. Another important aspect is security. Hardware-assisted virtualization improves isolation between virtual machines and helps protect systems from unauthorized access and security threats. It also mentions about shareable networking using technologies like VTC, which provide efficient communication and connectivity between virtual machines in a virtualized environment. These features together improve flexibility, security, and communication in modern cloud infrastructures. Hardware-assisted virtualization provides several important advantages. One major advantage is that it reduces the overhead caused by binary translation in full virtualization. Since the processor itself supports virtualization features, operations become faster and more efficient. It also removes the need for guest operating system modification that was required in para-virtualization. Because of this, unmodified operating systems can run more easily in virtual environments. However, there are some limitations. Hardware-assisted virtualization is supported mainly in newer generation processors, so older x86 and x86-64 systems may not support these features. Another disadvantage is that a large number of virtual machine traps can increase CPU overhead, which may reduce scalability and efficiency when many virtual machines run simultaneously. With this, we come to the end of Unit 2 on Cloud Resource Virtualization. In this unit, we discussed the fundamentals of virtualization, virtual machines, hypervisors, performance isolation, and different virtualization approaches such as full virtualization, para-virtualization, and hardware-assisted virtualization. These concepts form the foundation of modern cloud infrastructure and are widely used in data centers and cloud platforms today. Thank you.